Every time you explore a massive 3D world in a game like Cyberpunk or build a fortress in Minecraft, your computer is performing a constant trick. It takes that complex three-dimensional world data and flattens it into your two-dimensional screen. But how? The secret lies in a beautiful mathematical concept called projection. Today we are going to pull back that curtain on that. We'll start the old-fashioned way. Think of it as a manual computer graphics. We'll draw cubes and explore the core logic behind representing a 3D objects on a 2D surface. The intersection of a graphics development and an artistry, or technical drawing. Then we fire up a game engine to see the exact same principles digitally. If you are new here, hi! My name is Pavel, I'm a former graphics developer and researcher, and I hold a PhD in computer science. Today we are talking about computer graphics. If that's a topic you enjoy, don't forget to check out the playlist I've linked along with more videos right here on my channel. Okay, welcome to my desk. This piece of paper is our computer screen, our view plane. And this cube I'm about to draw exists in an imaginary 3D space we called world space. Our job is to map that 3D cube onto our 2D paper. First up is parallel projection. Imagine a world with no sense of distance, where objects don't shrink as they move away. That's the idea behind parallel projection. We start with the front face of our cube, a perfect square. Now comes the illusion to creating the third dimension. From each corner, or vertex, we draw a receding line, often at a 45-degree angle. The key rule is simple. All of these lines must stay parallel to each other. They never ever meet. And there we have it. It looks 3D, but a little odd, right? This is an oblique projection, a type of parallel projection. Another common type is isometric projection, which is fantastic for technical blueprints and stylized games like many old-school RPGs, because it preserves an object's proportions. But here's the catch. It's not how we actually see the world. That's why we need a different kind of projection. The one your eyes are using right now. To see the world realistically, we need perspective projection. The idea behind is simple. All lines that move away from us appear to converge at a single point, or sometimes multiple points. We call these the vanishing points. Let's start with one-point perspective. I'll sketch the front face of our cube. I'll draw a horizon line, that's our eye level, and place one vanishing point on it. From each vertex, I draw a straight line to that single vanishing point. Instantly, we get the illusion of depth. Our brain falls for it immediately. It's just like looking down a long, straight railway track. That's one-point perspective. But what if you rotate the cube and look at it from an edge? For that, we need two-point perspective. Here, we place two vanishing points on the horizon. We begin with the cube's front edge, then connect its ends to the both vanishing points. All horizontal lines now race toward one of these 2 points, creating a more dynamic and natural view. Next, we add vertical lines and repeat the process for the new vertices. Simple. Now notice this. If I move the 2 vanishing points closer or further apart, the cube changes shape. In computer graphics, photography for instance, we call this the field of view, or FOV. If you really want drama, like staring up at a skyscraper, you add a third vanishing point, either high above or deep below. This exaggerates the scale and makes everything feel massive. Let's start by drawing the first edge. From there, we connect it to the vanishing points and extend the shape just as before. Just remember that this time, instead of keeping the vertical lines, we'll use the third vanishing point. For a cube, 1-point perspective starts with a square, 2-point with a line, and 3-point with just a single point. So, drawing shows us the principle. Now, let's see it in action on the screen. Alright, here we are in Godot. We could use just about any program that can render 3D models. I've set up a simple scene, one cube, and a camera node. This camera is our virtual eye. Right now, the camera is in its default state. If I select the camera 3D node and look over in the inspector, you'll see its projection property. It is set to perspective. Notice the foreshortening on the cube. The back edges look smaller than the front edges, just like in our perspective drawing. Now, keep your eye on the cube. I'm going to change just one setting from perspective to orthographic, and all perspective is gone. The cube looks flat, its proportions perfectly preserved. This looks somehow like our first parallel drawing. Orthographic projection is simply a subtype of parallel projection. Okay, let's switch back to perspective. Here's the question. How do we control how much perspective we get? In our drawing, it depended on where we place the vanishing points. In the camera world, the lenses. In digital world, it might be this slider, FOV. The wider the field of view, the more distorted the cube becomes. A low FOV is like a zoom lens. It compresses distance and flattens perspective. A high FOV is like a wide-angle lens. It exaggerates space, stretches edges, and creates a dramatic effect. And that's the magic of projection. From the simple geometry of a pen and paper to the click of a setting in a game engine. You can even draw cast shadows using the same principle. So go ahead, pick an object around you and try to draw it. Experiment with different projections, it's surprisingly fun. For a start, keep it simple, work with straight lines and skip curves for now. And here's a fun fact, we are not limited to 3 vanishing points, you can have more, but things get strange very quickly. We might explore that in the future video. If you enjoyed this and want to learn more, hit that subscribe button. Thanks for watching and see you next time.